Right, I'm going to be talking through this paper comparing test sets with item response theory out of Amazon, New York, NYU, and the Allen Institute. So the broader idea here is we have different data sets that we test our models on, right? Think of like QA data sets, things of that nature. And some of these data sets are more useful than others if we want to, say, differentiate performance, right? That is how we tend to establish state-of-the-art performance, things of that nature. What this paper aims to do is understand which data sets are actually going to be, one, most discriminative for getting a sense of state-of-the-art model performance, as well as looking at a couple of other parameters for data sets to evaluate how useful they actually are for making the sorts of claims that a lot of new model papers make. More specifically, what they are doing is they're applying this item response theory. So item response theory is a statistical framework from psychometrics widely used for the evaluation of test items in educational assessment. More specifically, it is a model that aims to integrate three different concepts. So one is difficulty. How strong does a model have to be to get an answer right? Two, how effective is an example for differentiating between similar models. And three, guessing how likely a weak model is to get the example right for spurious reasons. So in that guessing example, for instance, you can imagine binary classification tasks are going to be easier than, say, span selection tasks, where I could very easily get the entire data set wrong guessing one thing. Binary classification, I guess one thing, hey, 50% of the time, I'm going to get it right. And then, discrimination, you can imagine a case when a particular data sample is going to have different answers for different models. That example would be discriminative. And then lastly, difficulty, you can imagine a case when a data set just has examples that everybody gets right or everybody gets wrong. Understanding these sort of three ways of looking at data sets, we can understand some things about how we actually consider these data sets to mean things about model performance and how strong they are. So I'll cover this item characteristic curve here. So what they're doing is they're taking parameters for an equation, which I'll share down below, but we measure the ability of a model on the basis of these three parameters. We're going to define P theta as the probability of a correct answer for a given theta, and theta measures the model's ability level, higher being better, more ability, we get more correct answers. What is the shape of this though? It really depends on a number of factors and depends on what models we're actually looking at and how well they perform on downstream data sets. So let's look at that equation here. So you can see the definition here. They have the guessing parameter, the difficulty parameter beta, and the discrimination parameter alpha. And this is how we're going to define the probability of getting item J correct. What we're going to do is use variational inference to infer IRT parameters from model response patterns, because we can obviously get to the probability of individual I answering item J correctly. But yeah, as far as these parameters go, that's a different story. So they walk through that. I won't get into the dirty details there. But yeah, we are then going to cover a number of different data sets. I think they have 29 in total that they look at. And then they are also going to only look at data sets where the best reported model performance does not exceed estimated human performance, because those are the data sets we obviously care about for doing state-of-the-art things. So the next thing that they get into, which I definitely want to touch on, is how they actually understand item characteristics. So they have this locally estimated headroom score. This measures the ability of each test example to contribute to the evaluation of near future progress. So the way they define this is the derivative of the example's ICC, with respect to the highest latent ability score, which corresponds in this case to Albert. So that sort of makes sense then, right? We want to understand how ICC changes with respect to ability, and specifically we're going to look at that corresponding to Albert, the best, biggest model we got. A high LEH score indicates that the best performing model is still far from the example saturation. So I'll just scroll back up to this curve really quick. Hopefully that makes some intuitive sense here. How we go from calculating the local slope of the ICC, the item characteristic curve, to get a sense of how an example at the ability level corresponding to the best model is performing. How much more headroom is there for it to improve, right? So going from there, we can actually generate some pretty quick answers to this question. So this is just looking at the LEH, locally estimated headroom, for all the data sets that they're testing. And we see some things that I think make some sense here. Hellaswag is a relatively complex data set, hence it requires that there's a lot of headroom to be had on that. Other data sets, SNLI, I'll touch on this a little bit more, not as much work needed there, especially because you have limited responses. So outside of that quick intuitive check on things, I want to get a little bit more into the dirty details here. So what they observe by looking at LEH scores is that QuoRef, Hellaswag, MC-Taco have examples with the highest LEH scores. This means that there is sufficient headroom for future state-of-the-art models with a higher ability to achieve better performance on these data sets. SNLI, when I mentioned, Commitment Bank, and MNLI have relatively low LEH scores, indicating that performance on these data sets is largely saturated. This is great, but they have a lot of other dimensions by which they are looking at this. So they want to look at the distribution of test examples according to the discrimination and difficulty parameters. They show this in figure 4. So data sets with span selection, so all these QA data sets basically have the highest discrimination scores than other data sets. Again, discrimination, let's just say, okay, bad models do bad, good models, bad models do poorly, good models do well. So highlighting span selection is an effective task format for discriminating among strong and weak models. As the span-based format restricts answers to be text spans in the given passage, there are concerns that it rarely requires reasoning ability, which often involves answers not mentioned in the passage. This is something that definitely provides some cause for concern, but on its face, it makes sense. For the difficulty parameter, they don't observe a narrow task format that is superior to others. So they show this here. So the span tasks on that first point are highlighted here. The difficulty parameters, as you can see here, that is something that is much more variable across different data sets. And I don't think that there's any clear indication that any particular data set is worse or better just across the board, and as opposed to the case when we can get discriminative capabilities for these QA data sets. So they make an interesting comment here that training set size and creation date do not seem to correlate with either examples, difficulty, or discrimination parameters. So that the whole idea of, oh, hey, this old data set was not sufficient, let's create a new one, this sort of puts that into question, right? So let's see. They also have an interesting graph in figure 5 where they show the distribution of examples jointly according to their difficulty and log discrimination parameters. So they have this half moon shape pattern that comes about. So looking at this, log discrimination versus difficulty, what this means then is that there's a wider range of discriminative sort of capabilities for particularly difficult examples and particularly easy examples, which I think is a pretty interesting finding. The other way to also look at this as well, which I think is clear, at least in some of these examples, is that there's a concentration in high difficulty and low difficulty examples in the data set. And there's not as many that are sort of in between, which I think is pretty interesting. Obviously, in some, not all cases, but the banana half crescent shaped ones, that does tend to be the case. We made one other interesting comment that I want to highlight here. And yeah, so for these multiple choice, sentence level multiple choice, they mentioned that there's a higher density of difficulty examples, while for other data sets, the distribution is more distributed. So more specifically, like looking at Winograd, I think that this is, or Winagrand, I think that that is like a pretty interesting finding, that, there might not be as much discriminative ability I think that might have something to do with the level of difficulty, although, that's not necessarily as high as, say, ArcC or ArcE, or some of these other data sets. It doesn't arise to that level, which I think is interesting, for sure. So beyond that, they have some, like that. This is just super valuable to just know, have these numbers out. So fitting ICC on examples that have only correct responses or only incorrect responses, discrimination parameter unconstrained. These examples make up 4% of their data. And there are 13 of the 29 data sets that contain at least one example. Roughly 16% of NewsQA examples are incorrectly answered by all models, while the remaining 12 data sets have less than 10% of all correct or incorrect examples. I would love to know more about what these 16% of examples are. They do a little bit of analysis on that, which I think is cool. Would be interested in sharing more about the appendix later. So I think that is mostly it. Yeah, they observe a positive correlation between ability and average model accuracy. But yeah, they run this qualitative analysis that I would definitely be interested in chatting more through, because these are just super interesting artifacts of these data sets that could tell us a lot about, one, what models know, and two, how good these data sets are for proving out future state-of-the-art work. So looking forward to discussing more.